All right, let's do this problem called all paths from source to target. Let's have a read. Given a directed acyclic graph DAG of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1 and return them in any order. The graph is given as follows. Graph I is a list of all nodes you can visit from node I. That is, there is a directed edge from node I to node graph. Okay, whatever that is. So this is the graph, and their output is 0, 1, 3, 0, 2, 3. Okay, what do we have to find exactly? Find all possible paths from node 0 to, okay, so from the first node till last nodes, return all paths. So in this case, from node 0 to node 3, this was one path, this was another path, fair enough. Here you want to go from node 0 to node 4. So 0 to 4 is one path, 0 to 3 to 4 is another, 0 to 1 to 3 to 4 is another, 0 to 1 to 2 to 3 to 4 is another, right? All of these different paths. Okay. So what exactly do I gotta do to get the different paths? Obviously, I have one of the things is I can do is I can start um a DFS, like do any traversal, either a DFS or a BFS, and from zero. And then whenever I reach four is where I will add that current path uh, to the end to the list, right? So for example, I start my DFS from zero, and one of the child is 4, so I already reached 0 to 4, so that is one path I'll add. The other child is 3, I can reach from 3 to 4 as well, so I'll add that as well. Then the other child is 1, from 1 there will be 3 4, from 1 there will be 2 3 4. All of those I'm gonna be adding um, into the tree, right? So let's keep track of current path, and whenever your current node is the end node, add that as the uh, add that node into the list. Let's try that. How is it represent? What is other things given? The input graph is guaranteed to be a DAG. All the elements of graph of I are unique. Graph ij not equals to I, that is, there is no self loops and some other stuff. Okay. So this graph is, what does it indicate? A list of nodes you can visit from node I. So graph equals to 1, 2, 3, 3, 0. Okay, so it is essentially an adjacency list. So from 0 you can visit 1 and 2. From 1 you can visit 3. From 2 you can visit sorry, from, yeah, 2 you can visit 3. From 3 you cannot visit anything. So that is essentially adjacency list representation already. So all we gotta do is let's see. So list and list of integer. So we add and we remove items. So let's use like an array. Let's use a list. Let's call it integer. So let's first build the result, right? So it will be a list of of integer. We can call it paths equals to new array list, and eventually this is what we will be returning. Let's also take a current path. So list of integer. Let's just call it path. So we're also taking a path, and now we're gonna do is just a DFS from, this is a graph, and we're doing a DFS from node 0, obviously, and we're gonna pass in the path, and what else do we need? I think that's it. So let's do this. So we do DFS. Let's take in the uh, graph. Let's take in the call it node, and let's take this as path. And now I'm gonna do something like so you do to begin with, you're gonna check if this node is not already in the path, right? That's one thing you wanna check. So if already in path, which would mean what? Which would mean so let's first do the target node. So target node would be if the node equals to um, a path or sorry graph dot size. It's called length -1. If this is the last node, so that's another question. Would the last node always not have a path from it? Yes, that is the thing. Okay, so last node never has a path going away from it. All right. So that is the case. Then that means you've reached the last node, and if you've reached the last node, you would want it to. Okay, so maybe for the last node, let's do simple. Let's do simple stuff. So first thing is if it's not in path. So if okay, so then you can't keep a list then. Um, if it's not in path, because cycles can be there, but you don't want to go with the if it's not the last guy. But hold on, do I even need this path if there are no cycles? It already says there are no cycles. Then okay, then I don't need to maintain anything like that. Okay, so I'm just gonna do path dot add the node. So I add this, and at the end of it, I'm going to remove it as well. So here I'm gonna do path dot remove node, and in between I'm gonna do for each. So for each neighbor in graph node, you're gonna do a DFS graph no neighbor and path, and at any point if so now at any point so we have, so as for example now let's consider this path 0 1 2 3 4. So I would have gone from 0 to 1 to 2 to 3 to 4. I would have added 4 into the path. 4 will not have any child, which is this. Then before removing here I'm going to do if um, node equals to graph dot length -1. I'm going to add this into the list. So I'm going to do, so this is what I'm something I have to pass as well then. I can maybe make it a global then. If I don't want to pass, I can do this. I can do, so I can do paths dot add new array list based on the current path. I add this current path into this list. And yeah, so let's run it. Index out of bounds. Okay, so you have to give an index. So you give path dot y is -1. You're removing the last guy. All right, it works. And for the example test cases, to see if it works for the second guy, it does. Let's submit, and it works as well. All right.